Hello everyone, hope you're doing well. My name is Mahmoud Kiasari and welcome to the extra chapter that I just promised we had about the matrices. For the previous chapter, we were talking about the matrices, we were talking about how we can denote them, how we can address them. It's a couple of rules and laws related to the addition, subtraction, multiplication. We also talk about the determinant or how we can use it in order to invert some kind of matrices. We talked about the equations, two unknowns, and three equations, three unknowns. As I just promised, apparently for the last part, we talked about too much of detail. So I rather to have another video for you in order to completely understand what has happened, and we are going to review all of the parts just some very shortly. Then we are going to solve some kind of examples that are related to that in order to make sure you completely understand. Again, first of all, if you haven't watched the previous video, previous chapters, try to watch them. Probably should be 2 chapters related to matrices. Watch them exactly as the way that I just explained, completely understand it, try to solve all of the kind of examples that we had before, then come to this part. And the way that I would like to complete this video would be active. Grab the pen and paper, then try to pause the video before any example that I'm solving. Try to solve it by yourself based on the previous knowledge. If you found it out, that would be perfect. If you didn't, try to watch the video as some kind of redo this process to make sure that you are actively learning, not just passive. Be active. So without further ado, let's talk about it. So if you guys remember, when we were talking about the matrices, the very first thing that we talked about is that most of the time, if you would like to denote a matrix, it was used for something like A, B, C would be capital. But if you would like to address a specific element, by the way, element means that each of these guys would be considered as elements. If you would like to address the elements, you would use the smaller version. So at this point, I do have the matrix, and its one would be 2, 5, 7, 1. So based on that, we know we have 2 rows and 2 columns, A2, 2. And what are the values of A1, 2 and A2, 1? It means that right now I have to look for the row number 1 and column number 2. So this guy would be row number 1. And since I'm looking for the column number 2, this guy would be it. So 5 is my answer. Then I'm looking at A21. It means that right now I have to go to row number 2 and column number 1. So it is somehow the vice versa. Row number 2 means this guy, and column number 1 this guy. Interaction between these two things is going to give me the number that they will like, 5 and 7 itself. Simple as that. Then we were talking about different kind of matrices: zero, identity, and diagonal. Also, we must mention 2 other parts. The one was about the upper triangle and some kind of a bottom triangle. We talked about it. So at this point, I'm trying to talk about 3 important parts that mostly you're going to use. Matrix. The zero matrix was the one that all of the variables in it was some kind of zero. It means that it has additive identity. It means that if you add it with any kind of matrix, they won't have any change or effect over your matrix. And at the end of the day, your matrix is going to be just intact. Imagine that I do have the calculation 3, 8, -1, and 5. I would like to add it with 0. By the way, we know we can do this addition because the dimension of both of these guys are the same. And you guys remember, it means that I can do the addition and subtraction if I make sure this dimension about the row and columns would be the same. So if I just do this addition, as you can see over here, if I add 0 to all of these parts, nothing would change. And the final result would be stay as the same it was for the first matrix. Another matrix that we have is identity matrix. Identity matrix means that the only matrix, that square matrix, by the way, square means that the number of rows and columns would be the same. The number on diagonal would be all 1. Rather than that, everything else would be 0. So at this point, if I do this multiplication, you guys know about that, how we can do the multiplication, right? It means that we do have the row 1, column 1, row 1, column 2. So at the end of the day, I would have a 2 by 2 matrix as my answer itself. So let's look at the first number. Well, the first number would be A, B, C, D, like this one, right? So I would like to find the A. How I can do that? 3 times 1 plus 8 times 0 would be 0. So I do have 3 as my first number. Then for the second number, 3 times 0 would be 3 times 0. And after that, 8 times 1. So my final answer would be what? Would be 8 itself. So this guy was 8. So we had it at 3. The second guy was 8. The third one, times 1. and 5 times 0 would be what? -1. And finally, I do have -1 times 0 and 5 times 1, so it would be 5 itself. Simple as that. So this is the result. As you can see, it is completely unchanged. That's why we call it as identity matrix. Finally, we do have a diagonal matrix. The diagonal matrix is the one that in the diagonal part has any number rather than 0 itself, while on other parts, on the upper section and bottom section, we do have completely 0. So the very first rule that we learned about adding and some kind of about the dimension of matrices was that, first of all, the definition of dimension. Dimension means that how many rows and how many columns you have. The dimension rule says that if you would like to do the addition or subtraction operation, first of all, you have to make sure that the dimension of both of your matrix would be the same. For example, at this point, I'm going to do the addition. First of all, I have to make sure that I can do that. Since I do have 2 by 2 and I had 2 by 2, I can do this addition simple. But on the other hand, I do have another one that I do have it as 2 rows, 3 columns, 2 by 3, and this guy would be 2 by 2. Obviously, I cannot do this addition, so it's going to be not allowed, some kind of arithmetic operation. Another thing that we have just talk about the normal arithmetic operation, addition. It means that we checked that our some kind of operation is possible. So the only thing that we have to do, we have to add the aligned or the same address in both of those matrices. It means that 9 plus 6, 2 plus 1, 5 plus 3, and 4 plus 8, and finally we do have the number. Simple as that. Nothing is strange, nothing has happened before. And on the other hand, we do have the matrix subtraction. Still, we have to check that both of dimensions are the same, and again, we are going to do this subtraction like the way that we had. It would be 1 subtracted from 4, 5 subtracted from 8, 2 subtracted by 3, and so on and so forth. And finally, if you do all of that, you do have this one as your final answer itself. Simple as that. Another one that we had was about scaling a matrix. What would happen if you do have the multiplication of a scalar part of and just a number by the matrix itself? It's just like the distributive rule. It means that when I do have the matrix and when I do have only one number beside, it means that I have to multiply that specific number, that this point is 3k, it could be anything, by each of those elements and write it down. It means that 3 times 2, 3 times 5, 3 times 7, 3 times 1, and I do have my final answer. So I'm going to multiply this guy by all of those elements or terms inside of that. Another thing that we have was about the distributive law. The distributive law is saying that k times a plus a and b are going to be matrices is equals ka plus kb, just like the way that we do have about algebra. Imagine at this point I do have k equals to 2 and a is going to be 1, 0, 2, 3. By the way, I told you this way is another way that most of the time we some kind of use it in the softwares because they don't have this way of definition of matrix or matrices. That's why we use this one. 1, 0 means that the first row, 2, 3 is the second row. At another point, I do have 4, 1 as the first row and 1, 5 for second row. So I would like to somehow confess, or someone not confess, obviously prove that actually the left-hand side or LHS is going to be as the same as RHS. How we can do that? We are going to, instead of just doing this 2 times A plus 2 times B, we are first of all, based on the PEMDAS, we are going to find anything that we do have inside the parentheses. Obviously, just a simple add 1 plus 4, 0 plus 1, 2 plus 1, 3 plus 5, and then multiply 2 by all of the elements inside of that. If you can do that, you will do have this guy as your final answer. On another hand, we are going to use the distributive law. It says that 2 times A, the first matrix, plus 2 times the second matrix. Again, we are going to multiply this 2 by all of the elements, and then when we found out all of those numbers, we are going to add the matrices, and we see that LHS and RHS are okay, so we don't have any problem, and we don't have any problem with this law, and this law works. We had another thing about the transpose. Sometimes we have to look at our matrix from another perspective. What does that mean? It means that we have to change the position of rows and columns with each other. It means that we are going to flip a matrix orientation. Imagine that I do have a matrix. A is 1, 2, 3 as row 1 and 4, 5, 6 as the second row. So right now I would like to find the transpose, and transpose would be A to the power of t. How I can do that? By changing the position of rows and columns. It means that 1, 2, 3 at the beginning was just the first row, but right now is going to be the first column. In the meantime, 4, 5, 6 should has the same things. So 4, 5, 6 was the second row, so right now is going to be second column, and finally I'm going to have something like this. As you can see over here, this guy is going to be a transpose. At the beginning of the point, I had 2 by 3, 2 rows, 3 columns, but at the end I do have 3 rows, 2 columns. Another rule that we learned was that transpose of transpose is going to be the same as the matrix itself. It's somehow negative times negative itself is going to be positive. How we can prove that? Easy. Imagine that I do have 8, 7, 5, 9 as my A. First of all, I'm going to find the transpose. The transpose would be the changing the position of rows and columns. So 8, 7 was my row, right now is going to be my column. 5, 9 was my row, right now is going to be my column. Again, we are going to find the transpose of transpose. So right now, I'm going to make 8, 7 as my first row. And I'm going to make 5, 9 as my second row. As you can see, these two guys are completely the same. So we just confirm this is going to be a fact. Another thing that we have was about the multiplication, the row by column machine. It means that I will have 2 by 2, and I would like to have these two multiplied by each other. By the way, you remember that if I do have A that has, for example, m times n, if I consider that m is the number of rows and n is the number of columns, and B was P times Q, again, P the number of rows and Q number of columns, if and only if my n is equal, it would be equal to P, I can say that my final answer is m times q. So this is a fact. At this point, everything works, so I know my final answer is going to be 2 by 2. What should I do? Again, write it down. As I just told you, first row by the first column. 1 times 2, 2 times 1. It's going to give me 4, so 4 is the first term. Then, I'm going to have row 1, column 2. The first row, the second column, is going to be 1 times 0, 2 times 5, I do have 10 as the second one. We have to do the same thing for the second row. So 3 times 4 and times 2 by 1. So 3 times 2, 4 times 1. Again, by each term. By making sure that you are following some kind of alignment, the same path. You are not going to have any mistake about that. 3 times 2 plus 4 times 1 is going to give me 10. Cool. And the final one, row 2 and column 2. Do the same thing, we do have this. And this guy is going to be final product or final answer itself. So what would happen if we do have the 3 by 3 multiplication? Still the same. So as we know, we do have 3 by 3 times 3 by 3. And finally, and my product is going to be 3 by 3 itself. So the very first thing that we have to do, write down the first one, or the first matrix, is going to be 1, 2, 0, 3, 1, 4, 0, 5, 2. And I have to multiply it by the whole things. But I know, the only thing that I have to do, just do it one at a time. First row by the first column of the second matrix. First row by the second column. First row by the third column. Add all of that, and what? I do have, put all of that inside my matrix, and I do have my first row. So the first row, first column, 4. First row, second column, 1. First row, third column, 5. I have to follow the same path for all of them. Row, second column, second row, third column, and I can find the numbers. Finally, first row, first column, third row, first column, third row, second column, third row, third column, and I do have this one, would be my final answer, as simple as that. So another kind of view that we had about a multiplication was about the combination of columns. So at one point when you do have a matrix and you would like to multiply it by something that we call as vector, you can, instead of just do all of the things that I just told you, instead of just keep it like this. You do have some kind of, instead of just working based on column, based on row, we are going to work based on column. So 1, 2, 3 is going to be first column, 4, 5, 6 second column, 7, 8, 9 would be third column. So 2 is going to be multiplied by this guy, 1 is going to be multiplied by this guy, and 0 is going to be multiplied by this guy. Somehow we say 2, 1, and 0 are the weights of our columns itself. So if we do that, 2 times 1, 2 times 2, 2 times 3, and if we do all of that, add them up, you're going to have the final answer like this. So how we know that guy is going to be right? Because at the beginning of the point, we had 3 by 3. Finally, we had 3 by 1. It means that these two guys are going to cancel out, and my final answer is going to be 3 by 1, and simple as that. Again, you still can do the same that you did. You are going to finally have this guy by itself. I challenge you to do our common way and prove that these guys are going to be the same themselves. After that, we had a very interesting thing about the determinant. Determinant is a number that is going to reveal the matrix story. And what is the important part? The important section is going to that guy helping me in order to find the inverse of a matrix. So how we can find a determinant? It would be this guy multiplied by this guy. So 1, 2, 3. 4 times 3, subtracted by 1 times 2 is going to be 10. So I do have a determinant. One thing that I can learn from the determinant is that if your determinant is a number rather than 0 itself, I can use it in order to find the inversion or some kind of the invert of my a itself. What was the inversion? It means that a to the power negative 1. What was the formula? It was 1 over determinant of a. And I do have this guy. If I assume that my a at the beginning was a, b, c, d, I do have it as d, a, b, negative c. This is the common formula for that. So if I know that my determinant is a number rather than 0 itself, it means that my 1 over determinant is not going to be undefined. So that guy is invertible. On another hand, if I just find out that my determinant is 0, means that I cannot invert that guy itself. So solving this system with an inverse method. If you guys remember, from the two equations to unknown, we had two common ways, elimination and substitution. A third way that I told you was about using matrices and how we can do that. I talked about it in the previous video. Again, try to watch that one, but at this one, I'm going to show you in an example. So this is important that because based on our alignment, we can find an answer. 2x plus y is equals to 5. 3x plus 4y is equals to 10. So the first thing that we have to do, find this matrix. A times x is equals to b. A is going to be the matrix of coefficients. X is going to be my variables, and b is going to be final answer that I have. So I do have 2 and 3. I do have 1 and 4. So for the first one, I do have 2 and 1. For the second one, I do have 3 and 4. It is very important. X by x, it means that if you would like to write them down some kind of top to bottom, it would be 2x plus y equals to 5 and 3x plus 4y equals to 10. Try to write it down like this because this is going to help you to reach to this one faster. So times xy is going to be my variable, is going to be my answer. So you guys remember how we can find that x is going to be a inverse times b itself. The way that we are moving this guy to another side is like this one. So a inverse, the very first thing that I have to check is determinant to see that can I invert it? So it means that at this point I do have 5. The determinant of a, it would be 5 itself. Finding a inverse, 1 divided by determinant, changing the position of a and d, then make b and c as negative signs. So a inverse would be something like this. The only thing that I have to do, multiply by this guy. If you do this multiplication at the end, you have 2 and 1, and this is going to be your solution. Right now, you have to check that these 2 and 1 are going to work or not. So 2 times 2 plus 1 is equals to 5, check. 3 times 2 plus 4 is equal to 10, check. So this guy is working. So another application that I told you about, which is going to be the final application of our some kind of matrices, means that we have to use it 3 by 3 equation of some kind of 3 equations unknown, something we know as the Gaussian elimination. So this way it could be a little bit complicated. You still can follow up the past way that I told you about how you can combine the two of those equations and then find 2 other equations or derive 2 other equations out of the whole thing. And by using that, you can find 1 or 2 variable, and based on those, you can find the final variable. So this way it could be a little bit complicated, yet it's completely worth it. And again, I solved one question related to the previous some kind of previous video, but right now let's have another one. Imagine that we do have the 3 equation, 3 unknowns. Again, we have to write it down top to bottom like this one. So I do have some matrix of coefficients. I'm going to write down like this. 1, 2, negative 1, 1, 2, negative 1, 1, 1, 2, negative 1. Then I'm going to apply this final answer as another column. I'm not going to use it in another matrix. I'm going to use it in another column. Then I have to do something. What can I do, or what should I do? The thing that I have to do is that make this matrix to be something like this. 1, 1, for example, A, B, C, whatever, 0, and then I do have some numbers. They could be anything, like D, E, F. By having that, I know the final variable would be F. The addition of the second and time plus C times this final variable is E. I can find the second variable, and this is another equation for that. So finally, I can use it in order to find my all of variables. So how we can do that? We have to use a couple of laws. As I just told you, we can add 2 rows and some kind of replace it with another row, and we are not doing anything. We're just adding these two and making another equation, and we can get rid of one of them and put the variable or the one that we found out from the addition there. We can multiply everything of one row by a number. It still makes sure that when you multiply this side, you also have to multiply this side by itself. And by doing that, we are going to reach to something like this. Let's see what would happen. So the operation number one, the very first thing that we would like to do is that replacing the R2, this is R2, this is a new R2 by the way, by R2 subtracted by 2R1, right? If I right now, let me just show you what I'm going to do. If right now I subtract the I2 by 2R1, what would happen? First of all, what is 2R1? This is 2, 12. It means that I have to multiply everything in row 1 by 2. R2 subtracted by that. 2 subtracted by 2, 0. When negative 1 subtracted by 2, negative 1 subtracted by 2, negative 1. 3 subtracted by 12, negative 9. Check. That was my first operation. So as you can see right now, I'm getting closer and closer to the thing that I would like. Why? Because R2 just reached to the thing that I like, but apparently it has a couple of issues because I still do have negative 3, but remember, I'm not done yet. So the second operation seems that R3 has a problem because I would like something like this, but this guy is a problematic. So how can I do that? So the very first thing that I can do, reach to my mind, again, you can do your own way, but at the end of the day, make sure that you finally reach to something like this, is that I'm going to subtract R3 by R1. So what would happen? And I'm going to just get rid of that because I would like to explain what would happen next, is that R3 subtracted by R1. So 1 subtracted by 1, 0. 2 subtracted by 1, negative 1 subtracted by 1, negative 2. And 2 subtracted by 2 plus 6 would be negative 4. Cool. Let's see there's some kind of the third way, because right now I just reached to the 0, but still I need to have another 0 over here, right? So at this point I'm going to change the position of R2 and R3. I still can do that, right? I'm not changing anything. I'm just changing the position of my equations, and we will see why we're doing that. So the only way that we did was that just changing the position. Nothing strange and nothing crazy. The next operation would be about R3. Still we're working with R3 because at this point you see that this guy has a problem, but somehow if I can find a way to add this guy with 3, I can reach this thing that I would like. In the meantime, I have to make sure this guy doesn't have any effect over itself. So what is the row actually we can use? Exactly, R2. Because if I multiply R2 by 3, I'm going to have a row, and if I add this one with this guy or the last row, I'm going to reach to the thing that I like. As simple as that. So first of all, I'm going to find the 3 times R2 itself. So let's just have this one. Cool. So 3 times R2 is going to be what? Is going to be 0. 3, negative 6. Be careful to multiply everything by 3. Negative 12, right? So after that, I have to add this guy plus R3 and put it in again instead of R3 itself. So if you do that, you have 0. The way that we actually liked would be 3 plus negative 3 would be 0. And we do have negative 6 plus negative 1 would be negative 7. And it's going to negative 21. Am I done? So everything seems, unless that you don't pay attention to this guy. Because right now you have 1. I mean, actually you need 1, but you have negative 7. So what can I do? Still, I can divide everything by this thing that I want. It means that I can divide everything by negative 7. I'm not going to lose anything, right? But I'm going to reach to the thing that I like. Oh, sorry. Reach to the thing that I liked, which is going to be this guy, right? So let's do that. So if I divide everything by negative 7, it would be 0 times divided by negative 7 is going to be 0. Now 0 divided by negative 7 is still 0. Negative 7 divided by negative 7 is going to be 1. Negative 21 divided by negative 7 is going to be 3. So right now everything is okay. Why? Because I just reached to the thing that I liked, which is going to be this guy. How can I use that? Simple. I know this one is representing the third variable, which was z. So z is equals to 3. Simple. Then I'm going to use the second row in order to find y and z, y, because I already have the z. So the second row would says that y plus negative 2 times z, which we found out is 3, is equals negative 4. So y is equals to 2. Simple. Then I'm going to use this one. X plus y plus z is equals to 6. If you do that, you have 1. remember, try to check that to make sure that you already have your answer and everything is okay. So thank you very much for being here today with me. Again, we just had a couple of questions related to everything we were talking about for the previous chapter. And I believe right now you're completely sure and 100% ready to solve any kind of question related to that. So at the beginning, I had a plan to talk a little bit about advanced matrices, but right now I would say that why try to do that, because it is completely enough. You're not going to use that in advanced algebra, maybe in another part. If you need to use that, that would be another kind of idea, but right now I think is enough. But anyways, if you guys found out you need more teaching or you need more detail, just let me on the comment down below. Please share a comment and it will be so helpful for me. Thank you guys for being here with me. Have a great day, night, whatever. See you around.